This is the second lab for Physics 2211. So in this lab, we're observing Newton's second law, which states that the net force is equal to the mass times acceleration, and from this we know that the final velocity is equal to the initial velocity plus the net force divided by mass multiplied by the change in time. So here we have our observed model. We can see a crumpled paper ball falling to the ground, just being dropped from the hand, and here we can see the plotted graph and the chart. So we want to grab a few measurements from here. So at our time, we have our initial y value. So we move on to our computational model, and we don't want to include drag here. So we know that there's a non-constant force. So the net force will not equal 0. In this model, we are observing the weight force, which is equal to the mass times the gravitational constant times j hat, which is in the y direction. So we know that the net force is equal to this. So first we want to change in our code the mass of the ball and the initial position. And then we want to include the gravitational constant, which is 9.8 meters per second, and include our j hat to make sure that this is all in the y direction. Next, we want to update the velocity of the ball and the position of the ball. So we have our formulas. We know that it's our initial velocity plus the net force divided by the mass times change in t, and we know the position of the ball is the initial position plus the velocity of the ball times change in time again. So we know that our net force is equal to the weight force, which is the mass of the ball times the gravitational constant, and then again times j hat to get it all in our y direction. So here we run the model through, we run our code through, and we'll see in the model our position versus time graph, and we'll see that there's only one force acting on the ball. So here we have the final position versus time graph. Now we move on to our computational model, where we include drag. So again, we have a non-constant force, but this time we know that the net force is the weight force plus the drag force. So the drag force is equal to the drag coefficient times the speed squared. So our drag coefficient is negative 0.0014, and this was estimated using the model and our final position. So here we have the net force is the weight force plus the drag force. So what we want to change here is what our F net is. So we rewrite the code to include that drag force. Now if we run the code through, we will see that here we have the gravitational force, and then we will have very slowly up here you can see that the drag force is coming into play. So the code keeps running through all our time. Now we have here the observed, the model with drag and without drag. So without drag, we see that this has the largest change in position because there's no force acting against the gravity force. Here we can see that these two are very similar. There are a few discrepancies through video distortion as well. Our drag constant is estimated, so it is not perfect. So that's where those differences come in. So terminal velocity. Terminal velocity occurs when the drag force and the weight force become balanced, so our net force is 0 and the velocity becomes constant. Here we see without drag, and we know that there's no force counteracting gravity, so we will never reach terminal velocity. With drag, we can start to see that the terminal velocity is beginning to be reached. If it had dropped from a higher position, it may be reached because the drag is counteracting. As well, with initial velocity, it will still reach the terminal velocity because the drag force is counteracting.